Hey guys, real quick before we start, I'm live streaming on YouTube in 2 hours, so come hang out and chat.
Okay, it's game time. Let's do this. Woo! I hope I didn't break anybody's ears with that. Last thing we did on Game Maker was make most of a tornado effect, but I've been brainstorming. I've got some ideas. We're gonna make it way cooler. If you look at the floor, like the way the tornado just sweeps in a circle at the bottom, that's really weird looking. Actually, it makes me uncomfortable. I'm uncomfortable looking at this. So, what I'm going to do is probably use the exact same formula. It's a really good formula. It's just a nice curve. I'm going to make it so that the bottom doesn't move at all. And as you get further up the tornado, then there's a little more movement. Let me make it a little bigger for the guys watching on iPhones. So we've got our circular momentum, circular movement, which is being scaled by this max movement. So max movement, max movement. Rather than this, let's add another thing like a movement interpolator. So when I is 0, we're looking at the very bottom ellipse. And when I is number of bodies, -1, we're looking at the top ellipse. This is our Nino formula. Let's go back to Desmos and pull that up again. So y is equal to, and I is our x equivalent, so we're going to use x. X is to the power of power h, so we'll just say h divided by number of bodies. I'll just do b for bodies -1. Again, to the power of h -1. Our number of bodies in this example is 24. Power h is 1.8. Power h is 1.8. 1.8. Number of bodies is 24. And this is our graph. When I is equal to 0, the graph is equal to 0. And it slowly grows until we reach 24, which if I do y is equal to x, this line crosses at number of bodies -1. Probably what we want to do is just have it go from 0 to 1 and multiply by our max movement. I think it's just y equals x to the h. That's the really basic one. Yeah, this is the exact same graph, sort of, except it crosses at 1. So that's the dealio. And by the way, you might be thinking like, well, wait a minute, there's two variable values here. How is this the same graph? Actually, h is a constant value, and b is a constant value. So all we're doing is scaling the entire graph by multiplying it there. And actually, you can see this in action, right? So if I just evaluate this expression, it's like this crazy number. I'm gonna copy that. If I simply divide by that, you can't see it because it's the same graph, but that's all we're doing. We're just calculating which constant we need to match the graph, essentially. But I don't want that. I want this to just be x over h and call it a day. Okay, so this is going from 0 to 1. Power of I and then comma, whatever our power value is in this case is just, so actually we need a new power value. This is going to be power movement, so let's just call it power m. And we will start with a 2. It's just the basic value. Power m. And then this I is actually not what we want quite yet. This I is going from 0 to number of bodies -1. We actually want it to go from 0 to 1. So it's going to be I divided by number of bodies -1. So when I is equal to number of bodies -1, this whole expression will evaluate to 1. And when I is 0, this expression will evaluate to 0. And this is changing. Right, so when this is 1, we then have our maximum movement, which is the top of the tornado. And when it's 0, we have 0 movement. So the bottom will not move. And let's see how that looks. There we go, just like that. So because we did that, we've kind of reduced the motion quite a bit, actually. So probably what I'd like to do is increase that max movement, which we have right here. Start scrolling the mouse wheel. You can see the tornado starts to move faster. And that's probably going to be what we want. Maybe increasing the max movement. I'm also noticing, so like as I increase the wave precession, that's not actually making it go faster. That's shrinking the size of the sine wave that's being passed through it. I think in order to make it go faster without editing anything else, I'm just gonna have to change my t value. So I can say plus equals 2, and this will go twice as fast. Music makes it sound like you're doing a live YouTube tutorial. I am doing a live YouTube tutorial. And then the other thing I realized, so I said last time that I was going to bake the whole thing into a single sprite. I'm actually not gonna do that because I had a cooler idea, potentially. Okay, yeah, so increasing the time value is pretty good. We already have an equation for an ellipse. This is a really simple axis-aligned ellipse, so it's pretty easy to define it with a function. I think I'm going to actually make some custom particle effects that move around according to the ellipse. So later what we're going to do is take the ellipse out. So we're not going to be drawing the tornado like this anymore. We're just going to draw those particles moving around. And if I have enough particles, it'll look like a tornado again. You'll get the shape back. I'm going to hit a 5 here, and we're going to change the maximum movement. Wait, that looks so goofy. Okay. Everything in moderation, right? Oh, by the way, these numbers are kind of small, but this is the current value that I'm looking at. So when I look at this and I say, yeah, that looks pretty good. If I go too much, it looks super wacky. So now I can go into my create event with all my constant values and change this 6 to a 7.5. So let's just make this a simple 2x2 pixel thing. It might end up looking a little bit big on our right, but it's kind of okay. So let's get rid of these 2 blue pixels. And now we just have a bunch of like rough tornado colors. So in our tornado, we need a few things. Yokai Phoenix, how much more juice will be in this juiciest game? Literally as much as we can squeeze in there, you know? As everyone knows, juice is a compressible liquid, so we're just gonna squeeze all of the juice in there until it's like a touch from bursting. That's kind of where we're going with this. I'd like to get the size of the ellipse, and I'm going to have a number of particles proportional to the size of the ellipse. Got this width interpolator and our current width. I'm actually going to steal these and turn these into arrays, and then we can just access the arrays later. Width interpolator array, and we'll have current width array. And there's more efficient ways to do this in GameMaker, but this is all going into C# later, so I'm not going to concern myself with it. But we do need the same kind of for loop, so I'm going to grab this for loop. It's right here. And then I'm just going to grab this, get rid of those. Rather than set these values, I'm going to set the current index of each of these arrays equal to the value that we were using before. So this will be current width array at position I, and we're going to do that for all 3 of these places. Subway Surfers gameplay in the corner. That's a great idea. All right, enjoy your Subway Surfers in the background. I got hella distracted. What were we even doing? Max audience retention. Now I'm getting distracted by the Subway Surfers. No, focus. All right, so what we're going to have is an array of positions of particles. First of all, I'm going to have a constant up here, which is like of particles scalar. This is going to be loosely based on the size of the ellipse. So let me start at like 0.5 and we'll see where it takes us. Actually, let me show you guys some ellipse math real quick. Hold on a second. I wouldn't want to block the Subway Surfers content. So we have an ellipse of a certain size. That is absolutely immeasurable. Ellipse. And just to make the math easy, we'll say the width of this ellipse is 3 and the height of the ellipse is 2. If you want to get the circumference of a circle, it's normally pi d. If you want to get the circumference of an ellipse, so see ellipse, that is really similar. It is pi times the major diameter, which is the long section, plus minor diameter, the short section, divided by 2. So basically just the average diameter of the ellipse. So the actual circumference of this ellipse, I don't know why I said this is 2. So what we decided on last time was the minor diameter of the ellipse would be 1/3 of the major diameter, so 1. And the average diameter here is 1 plus 3 is 4 over 2 is 2. So 2 pi. If I wanted to double the size of my ellipse, so make it 6 by 2, then the average here is 4 pi. So the outer ring of the ellipse increases linearly with the actual size of the ellipse. So that being said, we can just not have to do any math on it. We don't have to square things like you would for area. And the reason I say that is because we're not going to be using the area for anything. We're actually going to be placing little particle dots all around the circumference of each of the tornado ellipses. What I want to do is have a number of particles proportional to the circumference of the ellipse. So we don't have like particles at the bottom that are just filled with particles. We want them to, and then like at the very top, there's just no particles at all. It's got to be few particles when the ellipse is small, and lots of particles when the ellipse is big. Number of parts is going to be our number of particle scalar times our current width. And just because you can't have a non-whole number of particles, we're going to floor this. So floor means if you have any decimal, it just rounds down. Now we're going to add another for loop, everyone's favorite, nested for loops. If j is less than number of parts, j++, and this is where we're going to create an array of all of the positions of our particles. Part ellipse array. So this array tells us which ellipse we're currently looking at. So we are currently looking at the ith ellipse. No, you know what I should do? I should make this a 2D array. If I make it a 2D array, then I can just index particles only from the array I'm looking at. Oh, will this game take a 5090 Ti Founder Edition to run because of the epic spinning? No, it will not. This is the most efficient epic spinning you've ever seen in your entire life. Right, the ith value of our part ellipse array is based on this, and the j value is the current part we're looking at, and we don't need a part ellipse array because that is the point of the I value. Instead, we are going to start with a radius. So, not a radius, sorry, an angle. So part angle array. And this is just going to be a random number from 0 to 360. So, actually I'm converting this to C# later, and I know I'm going to be using radians, so let's use radians now. This is going to be random 2 times pi. There's no way GameMaker uses tau, right? No, I didn't think so. It's not cool enough for that. So that's our angle. I'm trying to think if I want to pre-compute the position of the particle. I don't think there's any point in doing that because the very next frame we're going to have to recompute it if it's spinning around. So we got the angle of the particle, and then we're going to use part color array. That's where we made all those different colors on the particle here. So we've got all these different shades basically. We're going to pick a color at the beginning and never change that color, so you can actually easily watch the particle spinning around. This is really easy. It's just random sprite get number, and that gets the number of subimages in the sprite I'm choosing, which is going to be sprite 2 in this case. I should probably have named that, but it's fine. Importantly, the GameMaker random function, this might trigger some people, does return the whole, so like, it returns the last number. If random 10 is greater than or equal to 9, this random value will sometimes return 10. So there's actually 11 potential values here, 0 to 10. No one did ask how my day was. Thank you very much. I had a really nice day. It was pretty good. I was excited to come home and stream after work, so here we are, streaming. Thanks again to everybody who is... Actually, I haven't thanked you guys yet. Thank you, everybody, for tuning into the stream. I hope you guys really enjoy it, and also hope you guys are having a great day. Yeah, this is just a GameMaker quirk. This minus, I'll have to remember to get rid of this -1 later, so actually, let me write myself a note. -1, because GameMaker random is inclusive. No inclusivity, please. Not in my code. So, if you don't know in Desmos, you can make parametric equations, and parametric equations kind of perfectly encompass what we're about to do here. So, if I do something like 1, 1, that gives me a single point. If I add t, so t is the constant, or sorry, t is the variable for time, it will show me an x and a y value as t goes from 0 to 1. So if x is t and y is t, then when t is 0, x and y are both 0. When t is 1, x and y are both 1. So simple as that, and every value in between. But we can do fun things with it, so if I do 2 times t, then we get a steeper slope, and you can see that when t is equal to 1, y is actually equal to 2. And we're going to use this for circles. So if I do something like cosine of t and sine of t, that will give us a circle with arc length 1. If I go from 0 to pi, it'll give us half a circle. And if I go from 0 to 2 pi, it will give us the full circle. Now, if I want to make an ellipse, it's really simple. If I want to make the ellipse wider in the x direction, boom, that's all I do. Add a 3. So this is our equation for an ellipse. It turned out to be pretty simple. The only thing to keep in mind, though, is while I put a 3 here, the actual width of the ellipse is 6, right? We go from -3 to 3. So the value I'll be putting here actually needs to be half of that. So both of these will be divided by 2. And this will give us the actual ellipse we would expect to see. So if I have a standard ellipse that is 1 unit, the way I'm doing things, that would be 3 across and 1 tall. What we want to do is get the value of our particle, we want to get the positions of our particle based on the current time. So right here, this is why I was saying it was completely analogous to what we were doing. We've got these t values here, that's just time. That's our time value. So we're going to substitute time in for both of these, and we're going to get our equation for an ellipse, and we're going to use that for all our particles, and everyone's going to have a good time and cheer and celebrate and go hip hip hooray. It is kind of making me want to initialize x and y positions for everything. So this is just initialization, so I'm just going to set everything to 0. This is going to be part x array and part y array. What's his name? Oh, he needs a name. Why don't you guys come up with a name? We'll give him a name. He can be our mascot for the day. Eric. Eric's pretty good. Okay. We'll go with Eric the ellipse. So for each ellipse, and then for each particle. So we can actually just grab this value again, right? Should I just make this an array? So for number of parts array, I'm gonna grab you. For j equals 0, j is less than number of parts array I, and then j plus plus. So j is now dependent on I, but that's okay. Okay, so first we have to update the angle. So this is going to be... Oh, actually, you know what I'm realizing? We need an angle. We also need a starting angle. So this is going to be... Oh, we probably want an arc speed for the particle as well. Yeah. So part initial angle array. And I'm actually going to steal this value. Part angle array can just be the same as our initial at the beginning. And then we want our part speed array. And let's do something like this. So I like making things dependent on the size of the ellipse at every part in this. So if you have a bigger ellipse in your tornado, it kind of makes sense that particles would be traveling faster around that one than your smaller ellipse. And we can do that really easily because we already have this current width array. So let's grab our current width array. And this might need to get scaled later, but for now it's fine. Actually, it's definitely gonna need to get scaled later because 15 degrees is insanely fast. And the max width is 105. That's gonna be quite fast. I might need to put this into something like a log function. So y equals log x. That's not what I wanted. Y equals x to the negative e. That's what I want. Now it does have an asymptote, but our starting value is 15, not 0. So we shouldn't run into something like infinity. So when this is 15.4, and when it's 105, it's 0.2. Maybe that's good. Maybe that's all I need. So this will be my scalar value. So we're gonna do power negative 0.3. But then what I want to do is have some sort of speed. So times random. I'm going to randomize the speed of every particle. And this is, so let's keep in mind here that at 105, we're going at 0.2 times. So if I set this to 10, then the actual speed is going to be like 5. So let's do like random 10. But I do want to make sure that we're always moving a little bit. So let's add a 0.5 on the off chance that we get random 0. Which actually, if we're going to be making hundreds of particles, that is not an off chance. Many of them will be at 0. Oh, actually, I guess that's not true because this is not integer random. So this will give us every single possible decimal value from 0 to 10. Okay, so we've got our starting angle, we've got our array, we have appliance direct, go away, our initial angle plus our speed times time. So as time increases, so too will our angle. Just to make sure it doesn't overflow, I kind of like doing this. We're going to, oh, I just realized I was doing this as if we were using degrees, not radians. This many radians, which is kind of silly, but I'm just copying and pasting, so it's fine. And then 0.5 is this many radians. We would have had particles moving so freaking fast. What I was saying was we would do modulo of 2 pi. So anytime this exceeds 2 pi, it's going to wrap back around to 0. Take another look at Eric the ellipse, and his function looks like this. So yeah, so t is our angle in this case, because we're using t to get angle, so it'll be increasing as time increases, just like in the graph. Current width times cosine of our particle, and remember, our current width is, if we apply current width here, it'll end up doubling the width of the ellipse, which is like the same thing here. Yeah, see, we always use current width divided by 2 to get the actual width of the ellipse rather than getting double the width of the ellipse. So we're going to do current width, and then we're going to divide the whole thing by 2. And then similarly, so in this case, we would Also divide it by 3 so that we have more of a perspective on the ellipse. And then we're going to divide by 2. So we can just combine those operations and divide by 6. And it's as simple as that. That should get us the position of a particle. Fun fact, so in another game, I didn't multiply a starting value by time when I was calculating position on an ellipse. And because of floating point error, if you spin the object like 600 times, it'll start to make the ellipse bigger or smaller, just because these numbers get to add up. But that's really stupid. You would never actually do that in the game. And if it really happens, there's a button to reset your view, which it's not meant to fix this bug. It's meant to be convenient and let you reset your view, because it was a puzzle game. But it's also a convenient fix for that problem.